Let's say you're making baby game dev's first RPG, and you're doing great, until you want the player to have an enemy to attack. It's really not that interesting if he doesn't fight back. Well, time to quit game dev forever. Just kidding. If you're watching this video, you've probably already tried implementing a basic solution. Stack a bunch of if statements in an update loop and call it a day. Voila, instant AI. Wait, what's this? Why is he doing that? Wait, stop! Stop! God, please stop! Please, no! No! Congratulations, you've built the leaning tower of if statements. The result? Code with more bugs than the Amazon rainforest at the end of the dry season. Unstructured code can work for small implementations, but we'll have to look somewhere else for complex behavior. Speaking of behavior,
behavioral trees.
That's a good trick.
Behavioral trees are interesting because they are both quite complex and quite simple at the same time. When determining a behavior, you start at the root and work your way down to what is called a leaf node. The leaf nodes are where the actual behavior is implemented. Everything between the root and the leaf are kind of like the equivalent of your if statements in the update loop. This is their simplicity. Their complexity comes from the construction of the tree itself. Building out a nice editor for behavior trees takes a lot of time, and hard-coding behavior trees is concentrated radiation poisoning on the level of Chernobyl. Luckily, Unreal has a built-in behavior tree editor, Unity has 50 different community behavior trees, Godot has Limbo AI and Behave. Anyway, the point is your game engine probably has a behavior tree implementation, whether it's default or community made. And if you have access to a behavior tree asset, you can get up and running very fast. Unreal's behavior tree even lets users watch the flow of decision-making in the tree itself as it happens. This highlights another advantage. Behavior trees allow less technically inclined developers to be able to modify AI without having to dive into code. This can potentially make them more appealing to larger teams. Oh, but what's this? You want the AI boss to have 7 abilities and 4 phases, each of which acts differently depending on their current health level, terrain, weather pattern, and star signs? Suddenly, your behavior sapling has grown into a redwood. Worse than the confusion, the bigger your tree gets, the more CPU power you need to run it. You can even get into behavior forests with things like nested trees, where you have a tree inside of another tree. At some point, it's just not clear-cut. But maybe it should be. State machines are goated. Here's how they work. You have a bunch of states like time travel, impersonate family, and terminate, and a state manager. The individual states are exactly what you'd expect, specific AI behaviors unique to a specific situation. What's important to remember is the states themselves control what state they transition to and when they transition to it. The state manager handles providing context to the states and switching between states. Enemy near? State manager lets you know. Need to go to a new state? State manager has your back. The simplicity of the pattern makes it easy to quickly implement your own code. It also remains performant, since at any given time, we're only concerned with the current state. Some people say that state machines don't scale well. I say nothing scales better. It doesn't matter how many states you have, you just have to follow what's happening in your tiny, modular, encapsulated box. If you ever need to debug anything, as long as you know what state you were in when things went wrong, you know where to start looking for effects. If you use event-driven systems, then most transitions between states are easily handled with subscriptions. This greatly limits the number of things we have to check for every frame. Not to mention, since it's all done in your own code, you get to feel like a gigabrain master hacker. But let's say this isn't dynamic enough. Let's say you want AI to more closely model reality and its behavior. You might be interested in GOAP, Goal-Oriented Action Planning. GOAP can be very, very complicated, but to distill it down to its basic essence, the AI is given a list of goals of varying priority. It determines the most efficient plan to reach each goal by A-starring its way through a list of actions. Each action in a plan is given a distance according to its difficulty to execute. If you don't know what that means, welcome to the hell of pathfinding. Multiplying the priority of the goal by 1 over the difficulty of the plan will give us the path which we should pursue. Oh, look at that. I forgot to optimize and now my CPU is 110 degrees Celsius. Well, at least it's not on fire. Anymore. Gope is favored by Monolith Productions, developer of Fear and Shadow of Mordor. It's complex to set up, complex in its results, and computationally expensive. This is good and bad, of course. System-driven games have been the example of some of the greatest masterpieces of gaming. On the other hand, they might be a little more bug-prone. A couple examples of good use cases are modeling ecological environments and turn-based strategy AI. But potential applications are truly endless. This is beyond a shadow of a doubt the most interesting approach to me. So it's really the best way to program AI behavior. In my opinion, state machines are the Swiss Army knife design. They can do anything you want them to, they're highly performant, and they're nearly infinitely expansive. But that doesn't mean they're the only solution. If you need something quick and dirty for simple behavior, unstructured does fine. Behavior trees are great for visualizing what's actually happening with your AI, and for less technical devs. I still think if you're working on your own game, it's better to prioritize learning coding, but the option remains open to you. Gope can create some really unique behavior, but has greater costs in terms of both development and performance. But this whole video is actually just a false quadcotomy, and behavioral trees and state machines can incorporate each other's subcomponents. And Gope usually implements state machines and behavioral trees by default. At the end of the day, you don't want any one thing handling too much responsibility. As long as your code is modular and encapsulated, you're probably doing well.